I will introduce my lab and myself. So I am Anirshu Divroy, and I am a junior researcher here at Admire Lab in the Carinthia University of Applied Sciences in Austria. So just a second. Yeah. Okay. So first of all, like our lab is very much diverse. Like we have starting from additive manufacturing to focus on medical technology, where we are focusing on wearables, lightweight technology. We are also in the area of robotics and sensors and how to optimize that. And then we have like in total 26 group members, 2 full professors, 1 endowed professor, 1 project manager, 8 PhD candidates, 2 senior researchers, 2 junior researchers, 7 master students, 1 center assistants, and 2 interns, and also 2 internal professors. And we have like various collaborations with different university like INRIA and also KIT. And so coming to the infrastructure, so our lab focuses on 3 different aspects. One is the material testing, the other is the 3D printing, and then we have the robotics. So for the 3D printing infrastructure, we have a Poland PAM series printer and a Haag 5-axis 3D printer. And yeah, like if you can see, we have the Poland one has a large elastomer compatibility. So the PhD candidates, they generally work on like trying to print different materials, understand their behaviors, and etc. For other than that, we also have few extra like different like industry built 3D printers like Markforged, Stratsys, and Race 3D. So coming to the main point, which is the AMASE. So AMASE is short form for Additive Manufactured Sensorized Prosthetic Liners. So the question arises, like, why do we need individual sensorized prosthetic liner systems? So first I will start like how is the prosthetic system works. Like so if you see the figure on the left, a person will have a residual limb. So for the residual limb, first there is a sock, which you can see in the figure on the right of, if you see figure C, the person is wearing a sock. So first they wear the sock on the residual limb, and then they wear the liner, which is made of a gel, like a strong, like a solid generally made of silicone, so silicone gel. And then we have the prosthetic setup, and it's in general the outside layer of gel is it's a hard prosthetic shell, which you can see in figure A. Is in general it's a very hard, it's a socket actually. So but there are various challenges in this kind of a system. So our proposal, once we want to get a printable, stretchable, capacitive sensor capable of 3-axis force sensing, able to understand the humidity and temperature of the, like inside the socket, what is going on, and also get a real-time feedback for the individual. So the main focus of the AMASE project here is to increase the usage of prostheses with comfort along with optimal rehabilitation. So by 2017, 57.7 million people were having limb amputation. Main cause of that is vascular disease, and some of them are like lower limb circulation disease. So these are the like reasons why, main reasons why people lose their limbs. Now, because of that, like the prosthesis they use the prosthesis, but the challenges of prosthesis is significant weight and close structures. There is the issue of like it's sometimes too tight or the fit is not proper. The temperature is not properly understood, like because in the summers or in the winters it can get really cold, or it can get really hot inside there and sweaty, it's bad. Then we don't have any sensory feedback. And lastly, we cannot focus on the clinical state of our residual, like the residual limb. We don't know what is the clinical state of the limb after the prosthesis. And if we are not aware of that, so you have the cause and the effect. So we have mechanical injuries, and it has so many problems. We have sweat, we have tightness, and each of them has its own different kinds of effects. Like if there is a bacteria formation there, so there will have different kinds of like skin disease and all those. So this is the general problems we are facing when a person is using a prosthesis. So just hold on. Why is it slow? Okay, sorry. Yeah, so our AMASE goals. So the AMASE goal is to develop a normal force and a shear force sensor using additive manufacturing techniques. The second one is we want to build sensor that can be directly integrated into the liner, which is, if you see the liner is the silicone gel which is worn after the sock, in a like, and which is like can be possible in a manufacturing, like we want to use one manufacturing setup, and with that manufacturing will make the gel as well as the sensor inbuilt into them as a single set, and we don't have to we don't want to focus on a two different step, like first we want to make the sensors and then we want to make the gel and integrate. No, we want to make it as a single setup. Then we want to understand what is the static and the dynamic forces acting on the residual limb. Then we want to add the temperature and humidity sensors. We want to integrate all of these sensors, the capacitive sensor, the temperature sensor, the humidity sensor, into a single liner, and then establish a digital twin for a prosthesis to understand what is actually happening with our limb and how the system is working. So first is the hardware and the hybrid integration. So we have like general core electronics, and we have soft materials which we want to integrate together to form like hybrid systems where we can, which will be flexible and which will also work as a soft electronic sensors. For that, we have some of the fabrication technologies which we are using, which is 3D printing of multi-materials, hybrid screen printing, EHD printing, and inkjet printing. So we use different kinds of printing to like see how can we like integrate and how is it behaving and what's the properties. So for the current progress of research, we have a sensor design and additive manufacturing area, where in the right, if you see, we have a few sensors which we have already designed for robotic fingers. And in general, for these are capacitive sensors, and we are trying to initially localize like how much is the touch and the localization force is working and how is it behaving. And secondly, the sensors which are designed is actually based on additive manufacturing techniques. So we want to make sure that these sensors can also incorporate the humidity sensor. If you see the bottom right picture, it's actually the humidity sensor, and we are trying to integrate all of them as a additively manufactured system. We also have a readout sensor, which is based on wireless transmission and capacitance to digital converter. Next, we have the material aspect. So for materials, the main challenge is to understand if the material is actually biocompatible with our skin. So our partners is actually, when first we are currently exploring what are the kinds of materials we can use. So we have found two of them. One is EcoFlex. EcoFlex is a soft biocompatible material, and it's washable, and it's perfectly insulated. So we have already established liquid metal connections to make the sensor to make the different active and the passive devices connect each other using liquid metals, and then use EcoFlex as a stretchable material. But still, we have to we will further go for biocompatible of the testing, like make sure that this one doesn't cause any like issues, because when it gets contact with the human skin in the long term. The next one is also another biocompatible elastomer, which is the PDMS, and PDMS is successfully printed on a flexible PET sheet, and we are trying to explore using PDMS to create electrodes, and how the electrodes and the pressure and the shear sensors is behaving, and that's for the material aspect. Finally, the digital twin technology. So we have our collaborators at the Indria Labs who are giving us the support with the SOFA framework. So the SOFA framework, as you see the figure in the light, we can actually make a replica of how our soft sensor is behaving as in a real time. So this is one of the examples of the SOFA framework, which is for a soft cylinder. The other one is the at initial system. We want to make sure that this same system is integrated. In the right, the figure is actually a fabric liner, which is used by our partners, Safinus Medical. But right now we want to integrate all the sensors and all the behavior into the SOFA, so that we and the prosthesist can be able to visualize how is the sensor and how is the force distributed, how is the sense, where is actually the force is working, how much is the force is working, is there is a change in temperature and everything. We want to have a real-time digital twin of that. So that's where SOFA framework comes in. So we are still trying to build a framework for that. And finally, what we want is a user-centric prosthesis. So we have the additive manufacturing techniques, we have digital twin, we have sensor readout, we have material selection, and we want to combine all of them, because the general idea is if you are a prosthetic user, you would want the rehabilitation to be based on the person's need. Like the main goal would be to someone who had a limb loss to actually replicate with a prosthetics that would be same, like close enough to the actual limb the person has lost. And for that, we need to understand what is going there, what kind of material, and what is the user's need. Like it might, the user sometimes happens that because of the amputation, the nervous system works in a very different way, because the it's not like a real leg. So sometimes people don't know what is going on in the process. So we want the prosthesist, the doctors, and all of them to understand and give a user-based, user-centric prosthesis. So for that, we need the sensors, we need to have materials, proper selection of materials, we need to make them very fast manufacturing, and it should not be hugely expensive, and then have a digital twin so that the prosthesis can be able to understand what is actually going on there, and then they can change based on the user's problems or user's needs. So finally, that's all for the presentation. And I would like to thank our partners, which is Silicon Austria Labs, who are also helping us fabrication in different kinds of fabrication, and Safinus Medical Technology, who is giving us the background of the prosthetics and stuff. So that's